Hey everyone, so here's your condensed version of chapter 3. I have a little racing to do. Let's go ahead and get started. So chapter 3 is about square root and cube root functions, and those have another name called radical functions. Radical because we have the check mark, which is known as a radical. And the first thing we're going to talk about are inverse functions. So I'm going to be doing just some straight reading from what you see here. But every relation, a relation is something you talked about in chapter 1. It's just a set of x and y ordered pairs. Every relation has an inverse, okay? And an inverse of a relation is a relation that undoes the relation. So the key point to this is you already know that inverses undo something. So adding has an inverse of subtracting. Subtracting undoes the adding. Dividing is an inverse of multiplying because dividing undoes the multiplying, etc. So if the inverse of a function is also a function, then we're going to write that new function with this notation here, f with that -1 of x, and it's read as f inverse of x. That -1 isn't an exponent, it just means it's the inverse. So if the inverse of a function is not a function, then we don't use this notation. All right, so let's take a look at our first example. Some of these arrows did not make it on here because we're going to draw them in there. So remember, domain are your x's, range is your y. I'm not going to fill this stuff out. I'm going to write them as an ordered pair. So x and y pair. Here's another x and y pair, and here's another x and y pair. And the questions I want to start to look at to decide is the relation an inverse function? I will ask myself these questions. So first, is the original relation a function? And the way I explain this to my students is I would check to see if it's a function, to see is each x unique, meaning does x not repeat? So if your x's do not repeat in this case, then yes, it's a function. Now, is this also a one-to-one function? Then I look at the y's and I want to see, are all of my y's unique? Meaning, do they repeat or do they not repeat? So all my y's are different. They don't repeat. So since they don't repeat, then yes, this is a one-to-one function. So from there, I can create my own mapping diagram of this. And what will happen is what was the range is now the domain. So that's another inverse. Range and domain can switch. And what was the domain is now the range. And I can just reverse these arrows here. So inverses are all about the opposite, like I said, adding, subtracting, multiplying, dividing. And now if I look at this as an ordered pair, so 7 with 0, 3 with 5, 6 with 2, this is a function. And not only is it a function, but it's also going to be a one-to-one function because none of my x's repeat and none of my y's repeat. Okay? All right, in our next example, looking at the first example, or this left diagram, if I start looking at the ordered pairs, I've got 3 goes with 0, 7 goes with 5, 1 goes with 5, 4 goes with 1. So is the original relation a function? And it is, because all of the x's are unique. Nothing repeats. Now, is the original relation a one-to-one function? So here I look at the y's, and the y's are not unique. I've got these 5s right there repeating, so the answer is no. So what happens if I switch this mapping back around, just switch the arrows. Oops, this one didn't show up. And I now write my ordered pairs, so 0 gets 3, 5 gets 7, 5 gets 1, and what is that? 1 gets 4. Then what you'll notice is my inverse is actually not a function because I have some x's repeat. So 2 things to take away from. Whoops, I don't know what that is. All right, a function. Oh, that's the wrong thing. Sorry. A function only has an inverse, which again we note this way, if the original function is one-to-one. So if the original function is not one-to-one, then the inverse is not a function. And then the other big takeaway is to know that the domain of the function becomes the range of the inverse, and then the other way around. The range of the function becomes the domain of the function. So basically, x's and y's interchange. All right, let's start talking about finding inverses. Did I leave anything else out? No, okay. So how do you find inverse? That's one big thing that we talked about. So you've got a couple things to do. Using the above facts, we can find the inverse of a function by, one, interchanging x and the y got cut off. I don't know where it went. And then we'll solve for y, and then we're going to write the function with our inverse notation. So first I just want to know, is the original function one-to-one? So if you did graph this, it would be linear. I would have a y-intercept of 1 and a slope of 1/2 that goes uphill. So I'm going to graph that really quick. Okay. It's a little hard to do on this tablet. I might be off a little bit. Okay, something like this. This is, again, not very easy to do. So that is 1-to-1. Another way I could check is it passes the vertical line test and the horizontal line test, so that makes it 1-to-1. So now that I know that the original function is 1-to-1, I will proceed to find the inverse. And the first thing I'm going to do is take my function, recognize that f of x is y, and I'm going to switch x and y around. And now I'm going to solve for y, because functions are normally y equals, and then y can be turned into f of x. So the first thing I'm going to do is subtract my 1. So now it's x subtracting 1 with 1/2 y. Now I'm going to get rid of my 1/2 by multiplying by the reciprocal. So I'm going to multiply all of this by the reciprocal as well. The 1/2 and the 2 cancel out. And then I'll just distribute the 2 through. Technically, you could leave it like that, but we will go ahead and do that. So that is my new function, and then I would write it in its inverse notation like this. So now what I'm going to do is graph this line. So I'm going to begin at -2, and my slope is going to be up 2 over 1. So just give me a moment. And now I have two functions that are inverses of each other. Okay, so let's try another one. We're going to find the inverse. So first, is it 1-to-1? Yes, it would be. I'm going to graph my line. So I'm going to begin at -6. I'm going to have my slope of 3/2, which goes uphill. So here's -6. So I'm going to go 1, 2, 3. Again, this is not easy for me to do on here. 1, 2, 3, 1, 2. I think that's a pretty good version of it. So that's 1-to-1. That means the inverse will be a function. So remember, g of x is y, and I'm going to switch x and y around. And now I'm going to get this new y alone, so I'm going to add 6 to the other side. So it's x plus 6 equals 3/2. To get rid of this fraction, again, I'm going to multiply by the reciprocal, so by 2/3. That means all of this is going to be multiplied by 2/3. The 3/2 and the 2/3 cancel out. You're just left with y. Distribute my 2/3 in. I get 2/3 x, and 2/3 of 6 is going to be, what's that going to be? 4. And then I can rewrite it with its inverse notation. And now I'm going to graph this one. So let me switch colors for this line. All right, so I'm going to begin at 4. And then I'm going to go up 2 over 3. Again, I'm trying to do this. Let's see. 1, 2, 3, maybe about there. Something like this. Again, these are not great lines. All right. So that is how you find an inverse. And then the next thing I want to point out, because this is going to be leading to our next thing, is visually, if functions are inverses of each other, then their graph, there is not spelled correctly, their graphed function reflects over the line y equals x. So if I graph the line y equals x, this is it highlighted, what you will see is a mirror image that the purple reflects the green over that highlighted blue line. So that's a very big thing to remember. Visually, they will reflect over the line y equals x. And how did I graph that so quickly? Just remember it's y equals 1 over 1 x plus 0. So there's my y-intercept of 0, and my slope is up 1 over 1. All right, let's move on now. Here's two more, just finding the inverse. Let's try something a little more challenging. So if we graph this shape, this is going to be a U. And if we graph this shape, well, you haven't gotten to this shape yet. It's actually going to look like this. So let's find their inverses. Technically, this one is not one-to-one because it fails the horizontal line test, but we're going to add something to it at the end. All right, so this is Y. Switching X and Y around. And now I'm going to get my new Y alone. So first I'm going to add 1 to the other side. That gives me X plus 1. And as I create an inverse, I'm using inverse operations. Then I'm going to divide by 2. So divide by 2, divide by 2. Moving this down here. Now to get Y alone, I will square root. And I'm moving on to the next page, but aren't I? So I'm going to write it here. So now I'm going to have the square root of all of this. You could put it in parentheses if you want. And then I have this Y plus 2. And now to get Y alone, I'm going to subtract the 2, which will not be in my check mark. And then instead of writing Y, I'm going to go straight to my inverse notation and do that. All right, so how do I make this function work if technically my original function is not one-to-one? So I'll just put a little restriction that regardless of what I do, that my x, that this is going to be greater than or equal to 0. All right, let's try the next one. So finding the inverse, and let me walk through this one a little more. I'm going to go ahead and just switch X and Y, around. And walking you through what I'm doing. So here is my order of operations, all of these inverses. So the first thing I'm going to do to get Y alone is undo the addition with subtraction. So it's going to be X minus 3 on the other side. There is no multiplication or division to get rid of because it's the square root of Y plus 2. So now to get rid of my exponent, or I'm sorry, my radical, I will use an exponent. So to undo a square root, I square both sides. And I'm just going to leave the left side as x minus 3 squared. I'm not going to do x minus 3 times x minus 3. And then what I'll do is get rid of what's left. There's technically not parentheses, but I will move that 2 over, which does not get to be part of the parentheses squared. And now instead of y, I'm going to rewrite it in an inverse notation, like such. Okay, let's try to wrap this up. This is our last part in this section, I think. If I can get, yeah, it is. Okay, so last thing is using composition functions. That is something you did, I believe, in a previous chapter already. It's where you take the function of another function, and what happens if you take the composition of the function and its inverse, and the other way around, your result that you should get when you simplify and clean it up is just x. And if you think about it, that hopefully makes sense, because if functions are inverses of each other, they reflect over that line y equals x. So what we're going to do is see, are these functions inverses of each other? So I will take composition functions like this and like this. Different ways to do this. I ended up explaining it to my students like this, that g of x is going to go into f in this first one. So we would start with that. So g of x would be replaced with what it's worth. And then this says go to f's function and substitute this in. So that's exactly what I'm going to do. Here's f's function. In for x will go the 4x minus 16, kind of what this arrow is showing. And then I'll still have the plus 4. And when I simplify this, I should end up with just x. So what I'll do is distribute my 1/4, which gives me x minus 4. Then I still have the plus 4, and then plus 4, and then those 4s will cancel out, so I just get to x. So we are on the way to showing one function is an inverse of another. So when I do the other version of the composition function, this says f of x is going to go into g of x. So over here, I'm going to replace f of x with what it's worth. And then again, this says go to g's function, put this in there. So I'm going to do that a little bit more over here, though. So where the x is, I'm going to put 1/4 x plus 4. and then minus 16, and then I'll simplify this, and when I'm done I should just get x. So I'm going to distribute. I'm going to get x plus 16 minus 16, those cancel out, and I get x, just like the line of reflection. So yes, these are inverses of each other, because in both situations I get x. All right, last one. Let's find out if they're inverses. So again, I'm going to take f of g of x, and I'm going to take g of f of x. And I know I'm going fast, but in the first situation, I'm supposed to take g, put it right in there. Or, here, writing it a different way, go to f's function, put this in there. So I'm going to do that. Inside my cube root will be the cubed root of x cubed minus 2 plus 2. And my goal is to get down to x. And unfortunately, I will not be able to do that because I cannot take the cubed root of all of this. Now, if it was just this, then yes, I could do that. I could take the cubed root of x cubed, get to x. So if the problem had presented this way instead, then the cubed and the cubed root would cancel each other out, and then the 2's would cancel out and I would get to x. But that's not what's happening here. So already I can see, because I changed the problem, I'm not going to get to x. No, that's not going to happen. And maybe you'll see it easier, better in the other version. So the other version says take f of x and put it into here. So that's what I'm going to do. All of that is going right where that x is, or go to g's function and put this in there. So in for x, I'm going to put all of this minus 2. And the reason why this isn't going to work is just for one more reason, is this third power actually means that there's 3 of these. And if you take your time and multiply these 3 parentheses, it's just going to be a mess and nothing's ever going to cancel out. So my answer is no. We don't tend to give a lot of problems where the functions aren't inverses of each other. Usually the answer is going to be yes, but every now and then we're going to give you a no answer. And that's your first set of notes.